So this video will go over section 8.3 on solubility. So let's start with general features. Solubility is the amount of solute that can dissolve in a given amount of solvent. It is usually reported in grams of solute per 100 milliliters of solution. So grams per 100 milliliters. So it's a value, it's the maximum amount that you can dissolve in a given amount of solvent. And here the given amount is 100 milliliters. So that solubility is a maximum value of grams of solute that can be dissolved. And so out of this, there is some vocabulary. And one of them is a saturated solution. A saturated solution contains the maximum number of grams of solute that can dissolve. So if you do have reached the maximum amount, then you have reached a saturated solution. And so the beaker here is showing you how solubility, dissolving of the crystals and recrystallizing of the crystals is happening. It's a dynamic process where, if more solute dissolves, and then there is too much dissolved in the solution, then some will recrystallize. And so it's a dynamic exchange between dissolving and recrystallizing. And so you can see in the picture here that the bottom of the beaker has a lot of undissolved salt there. So that's going to be typical of a saturated solution. The solution above contains the maximum, and so what's on the bottom of the beaker is what cannot be dissolved anymore. And so an unsaturated solution contains less than the maximum number of grams of solute that can dissolve. So in an unsaturated solution, you will not see crystals at the bottom of the beaker. Everything is dissolved, and you could even dissolve more. So it's allowing you to still dissolve more when it's unsaturated. So let's practice this concept by doing this learning check. So at 40 degrees Celsius, the solubility of KBr is 80 grams per 100 grams of water. Identify the solutions as either saturated or unsaturated. So solubility depends on temperature, and that's why temperature is given here, but you can see that in each case the temperature is 40 degrees Celsius. So what matters here is the solubility of KBr is 80 grams per 100 grams of water. So that's the maximum amount you can have for 100 grams of water. So for example, when you're told there is 60 grams of KBr added to 100 grams of water, you have to think, does it exceed the maximum amount or is it below? And so here we are adding that to 100 grams of water, which is what the solubility is using as a reference amount for the solvent. So you can just simply compare 60 to 80 grams, which is the maximum. And so here it's below. So that means you have not reached the maximum amount, so it's unsaturated. Unsaturated because the amount 60 grams of KBr in 100 grams of water is less than the solubility of 80 grams of KBr in 100 grams of water. So in the case B, we have 200 grams of KBr added to 200 grams of water at 40 degrees. So notice how this time it's in 200 grams of water. So it's not the same reference amounts as what the solubility gives. The solubility is 80 grams per 100 grams of water. So here we have 200 grams of water. So you want to take this into account and multiply the solubility by 2, because if you can put 80 grams of KBr in 100 grams of water, that means you can put 2 times 80, which is 160 grams of KBr in 200 grams of water. So the solubility is then 160 grams of KBr. And here we are trying to put 200 grams, which is above the 160 grams. So that means we have a saturated solution here. So the solution here shows you that instead of multiplying the solubility by 2, it's dividing the given amount here by 2. So instead of comparing to 200 grams of water, if we divide that by 100, so let's say we have only 100 grams of water and we are trying then to put 100 grams of KBr, because you divide that amount also by 2. And so it comes down to trying to put 100 grams of KBr in 100 grams of water. And 100 grams of KBr exceeds the solubility of 80 grams of KBr in 100 grams of water. So that means the solution is saturated. Now, in the case C, we have 25 grams of KBr that is added to 50 grams of water, still at the same temperature. So 50 grams of water is half of the amount that the solubility uses. So let's multiply 50 by 2 so that we have 100 grams of water. So if we multiply the grams of water by 2, we will multiply the grams of KBr by 2, and the 25 grams will become 50 grams of KBr added to 100 grams of water. And so 50 grams of KBr is less than 80 for 100 grams of water. So that means it's going to be unsaturated, because this is the same as 50 grams of KBr in 100 grams of water, which is less than the solubility of 80 grams of KBr in 100 grams of water. So some more basic principles about solubility. So one basic rule that you should always remember is that solubility can be summed up as like dissolves like. And what it means, it's like properties will dissolve, substances with like properties. And the property that matters the most here is polarity. And so solutions that are alike will be soluble together. For example, a polar solute will be soluble in a polar solvent. If both solute and polar are solute and solvent are polar, then they are soluble. Or if both are non-polar, solute and solvent, then they will also be soluble together because they are alike. And so that means your solutions will not form when your solute is polar and you try to dissolve it in a non-polar solvent. Or vice versa, a non-polar solute will not form a solution with a polar solvent. So like dissolves like, you want the same kind of polarity for solubility to occur. So let's go through examples. So solubility can be summed up as like dissolves like. And so in the case of water, the molecule of water, we know now that it's a polar molecule. And because it's polar, anything that is polar or ionic will dissolve well in water. So polar covalent compounds or ionic compounds will typically dissolve well in water because water is also polar. And the illustration here is showing you how salt, table salt, made of NaCl, it's an ionic compound made of sodium ions and chloride ions. And when you place it in water, it is soluble because ions are the extreme of polarity, and the water molecule will be attracted by the ions. So the ions will be taken one by one away from the crystals, and the molecules of water will orient their oxygen side to the cations. So here on the right side of the slide, you can see how the Na plus, which is the gray sphere here, is surrounded by molecules of water that have their oxygen pointed towards the cation, because oxygen is more electronegative and has a delta negative partial charge, and so it will be attracted by the positive ions. And the chlorides, which are the negative ions, they will be surrounded by the molecules of water, but it's the hydrogen side of the molecules of water that will turn towards the negative ion, because the hydrogen side of water are partially positively charged. And so this way, water is able to dissolve a lot of ionic compounds. Small neutral molecules that contain oxygen or nitrogen are also typically soluble in water, especially if they can hydrogen bond to water, which means if they can form a hydrogen bond with the hydrogens and of the molecules of water. So the illustration here is showing ethanol, a small neutral molecule that has a OH bond. And so these CO and OH bonds are polar. And because the hydrogen is bonded to an oxygen, it can do hydrogen bonding with the molecules of water. So here the illustration shows how the hydrogens of water is attracted by the oxygen of the methanol. But the hydrogen of the methanol that is bonded to oxygen is also attracted to the oxygen of molecules of water. So there's multiple possibilities for hydrogen bonding, and that's why methanol, a small neutral molecule that is polar, can dissolve in water. So now if we look at non-polar compounds, they will be soluble in non-polar solvents, right? Because like dissolves like, so they have to be of the same kind. And so a non-polar compound will be soluble in a non-polar solvent. And the illustration here is showing you how octane, which is made of 6 carbon and 18 hydrogens, so a long chain of carbons surrounded by hydrogens. And we know now that this is non-polar because the CC bonds and the CH bonds are non-polar. So this molecule is non-polar. And then the CCl4, carbon tetrachloride, is made of a carbon surrounded by 4 chlorines. The CCl bond is polar because chlorine is more electronegative than carbon. However, the structure is symmetrical. It's a tetrahedron, and the 4 chlorines are pulling equally with the same strength from 4 different sides that are all equidistant from each other. And so they will cancel out, this will cancel out all dipoles. And so overall, CCl4 is non-polar, even though it is made of 4 polar bonds, right? But the molecule overall is not polar. So we have octane, which is non-polar, and carbon tetrachloride, which is non-polar. Both are non-polar, so they will dissolve very well together. Remember how non-polar liquids will only exhibit London dispersion forces between themselves because they don't have any dipole and they cannot do hydrogen bonding. So they experience the same kind of intermolecular attractive forces, which is only the London dispersion forces in their case. And so then they will mingle very well together because they are all nonpolar and experiencing the same kind of intermolecular attractive forces. So a quick learning check here. When you have solid lithium chloride added to water, it dissolves because, and so you have to answer this question. And the first question is, the Li plus ions are attracted to the oxygen atoms of water, which are partially negatively charged, or the hydrogen atoms, which are partially positively charged. So what do you think? So here the answer is that because the lithium plus ions are positively charged, they will be attracted to the oxygen atoms, which are partially negatively charged, right? Opposite charges attract. So then the chloride ions are attracted to the oxygen atoms, which are partially negatively charged, or the hydrogen atoms, which are partially positively charged of water. And here, again, opposite charges attract, so the chloride ions will be attracted to the hydrogen atoms of water because they are oppositely charged. A more involving learning check here. So answer the question here. Will the following solutes dissolve in water? So you want to apply the rule that says like dissolves like. So remember that water is polar, right? Water is polar. And so if like dissolves like, so anything that is polar will dissolve in water according to that rule. So let's start with Na2SO4. Na2SO4 is an ionic compound, right? We know this because it's made of sodium, which is a metal, from the left side of the periodic table. And we recognize SO4, which is the sulfate ion, a polyatomic ion made of nonmetals only. And so together, sodium and sulfate are forming an ionic compound, which means that they are made of ions. And so water likes ions because that's the extreme of polarity. Ions is when you go all the way to a full charge, right? So ionic compounds tend to be soluble in water. Decane, C10H22. Is it soluble in water? So decane is a long chain of 10 carbons all surrounded by hydrogens to complete their octets. So it's only carbon-carbon and carbon-hydrogen bonds, which are all nonpolar. So we know now that decane, this kind of molecule made of just carbon and hydrogen, is nonpolar. If it's nonpolar, it's going to be insoluble in water because water is polar. So methanol, CH3OH. Methanol is just one carbon surrounded by 3 hydrogens and OH bond. So the OH bond is a polar bond and the CO bond is also a polar bond. So this type of bonding will not be, this type of dipoles, they will not be cancelled because around the oxygen you have a tetrahedral shape and it's bent. So those two bonds are bent and so the dipoles add up and you have a polar molecule here. And so because it's polar, it's going to be soluble with water. Cetyl alcohol. The formula is CH3, CH2 14 times, and CH2OH. So it's a very long chain of carbons and hydrogens, and we know that this is nonpolar. And then there is that OH bond. As earlier, we know that that part of the molecule is polar. However, we have a very long, a much longer part of the molecule that is non-polar and more cumbersome. And so it's mainly non-polar, so it's going to be insoluble in water. I2, iodine. It's made of two iodine atoms. And when you have two of the same kind of atom, it's making non-polar molecules, right? Because they pull electrons with the same strength. And so the electronegativity is 0 between two atoms of the same kind. So it's non-polar. So it will be insoluble in water. And then finally HCl. HCl. So this is an acid. And acids are very, even though they are made of nonmetals only, right? Because hydrogen and chlorine are nonmetals. Even though they are made of nonmetals only, and so they are covalent compound. Acids are behaving like if they were ionic compound, and they make H plus ions, and then here it's going to be a Cl minus ion. And so HCl in water will make those ions. And that means it's going to be polar, it's polar, right? Because if you look at the HCl bond, it's also a polar bond according to the electronegativity difference. So that makes it soluble in water. So one last word about solubility. There is tables that have been made from observations. So scientists have observed if ionic compounds were soluble or not, and they have established those tables that we call solubility rules for ionic compounds in water. There are many kinds of tables like that. They don't look the same, but they have the same information in the end. So that doesn't matter the kind of table you are using. They should all get you to find if a given compound is soluble or not. And so the general rule is that salts that contain at least an ion from group 1A, so the alkali metals, NO3, which is the nitrate ion, or C2H3O2 -1, the acetate ion, will be soluble. And there is no exceptions with these ions. They always make soluble salts. So soluble salts typically contain at least one ion from group 1A, nitrate or acetate. And so we have this table here showing us how the alkali metals like lithium, sodium, potassium, rubidium, cesium are always making a soluble compound. Ammonium is also making always soluble compound. And we just saw earlier the negative ions like nitrate and acetate always make soluble compound. And then you have some other ions like the halogens, the chloride, bromide, and iodide, which are mostly soluble, but there are exceptions with them. And so they are listed here. They will be insoluble when they are combined with silver, lead, or mercury. Same with the sulfate ion. It makes soluble compounds except when combined with barium, lead, calcium, strontium, or mercury. And ionic compounds that do not contain at least one of these ions are usually insoluble. So you have this table, but in your reference packet, so in your reference packet, if you look at the page where you have the names and formulas of common polyatomic ions, below that you have a table that is called the solubility rules. So It's a different kind of table, but it has the same information. But here it's split into two parts. The top part of the table says soluble ionic compound contains nitrate, acetate, and there is no exceptions when you have those ions. And they are soluble, the chloride compounds are soluble except when they are with silver, mercury, and lead. Same with the bromine and iodine. And then the sulfate ions make soluble compound except when they are with strontium, barium, mercury, and lead. And then the second part of the table lists the insoluble ionic compound, and these are mainly made of sulfide, carbonate, phosphate, and dihydroxide. But there are exceptions, which are, of course, when you have the alkali metals bonded to them. The ammonium ion is also making soluble compounds. And some more exceptions with calcium, strontium, and barium for sulfide or dihydroxide. So you need to learn how to use those tables and find out from these tables if your ionic compound is soluble or not. So if we go back here, let's do a learning check to see how to use this table. And I'll go directly to this page where we have the table reminded for us on the bottom of the slide. So let's predict whether the following compounds are soluble in water. So let's start with K2S. According to the table, an ionic compound is soluble in water if it contains one of the following. And so in the positive ions list, there is K plus there, right? Li plus, Na plus, K plus. So that means whenever you have K plus potassium, it's going to be soluble. Calcium nitrate here. So let's try to see if there is calcium. So calcium is not listed there. However, the nitrate is listed. An ionic compound is soluble in water if it contains, among the negative ions, there is the nitrate. And there is no exceptions. So that tells you any kind of nitrate compound will be soluble in water. So the calcium nitrate is then soluble in water. So PbCl2. PbCl2 is made of lead and chloride. The chloride ion, we can see it here. It's listed among the negative ions. So an ionic compound is soluble in water if it contains the chloride. However, we need to look at the exceptions because there are exceptions in the case of chloride, except when combined with silver, lead, or mercury. So that means when chlorine is combined with lead, it is not soluble. It's an exception to the solubility, and that's going to be insoluble in water. NaOH. NaOH is made of Na plus and OH minus. According to the table here, it says that an ionic compound is soluble if it contains Na plus, and there is no exceptions. So here we have Na plus in the formula, so it's going to be soluble in water. Li3PO4. Again, Li3 contains the lithium ion, which is another alkali metal, and all alkali metals are making soluble compounds, so that's going to be soluble. PbSO4. PbSO4 contains lead and sulfate ion, SO4. You recognize SO4. We can see SO4 listed here in the list of negative ions that make a soluble compound, but there are some exceptions. So we need to see if Pb is part of the exceptions. And so SO4 -2 is making soluble compound except when combined with barium, lead, calcium, strontium, or mercury. So lead is there. It's in the exceptions. So that means it's not soluble. Sulfates are usually soluble, but not when combined with lead. So that's going to be insoluble in water. AgCl. So here we recognize the chloride ion, and an ionic compound is soluble if it contains the chloride ion, except when combined with silver, lead, or mercury. And here it's combined with silver, which is part of the exception. So then the chloride will not be soluble in this case, and AgCl is insoluble in water.